Welcome to JFix and episode 4 on trying to fix the JDT laptop. Now, I can't believe this is episode 4. I think we're going to have to start calling this season 1 if we don't finally get to the bottom of what is causing this laptop to crash. So let's get straight back into the diagnostics again and see if we can move further with actually getting this repaired. So on the last video, I was trying to do some tests to find out if it was maybe the CPU or the GPU that was causing this laptop to crash when it loads into like a Windows environment. Now towards the end of the video, I did get the thermal camera out and have a look, under the thermal, what was actually happening. Especially I was looking at the CPU and the phases around the CPU. So we discussed a little bit last time about the power to the CPU and how we have the SoC and we have 4 separate VCC, the main power for the CPU. So we can see I've marked them up on here, 1, 2, 3, 4. These are the 4 phases. They are all in parallel. They've all got continuity between them. And when I checked under the thermal camera, only phase 1 was heating up. The other 3 phases had no heat in them at all, like they weren't even coming online. So I was thinking that maybe the CPU, when it's not under load in the BIOS environment and it's only using the one working phase, when you start doing something a bit more intensive, like trying to get into Windows and it demands more power, it's not going to be able to deliver that because only 1 out of the 4 phases are working. However, this might not actually be the case because BoardRev reached out to me and he messaged me and let me know, and a few other people have also mentioned this after, which I wasn't aware of, is that the PWM controller on this board does support phase shedding. Now, just because it supports it, it doesn't mean it's in use, but it's quite likely that what it will do is power saving. Just use a single phase until it needs it, and then it will activate those ones. So it could be normal behavior that only one phase is heating up and not actually a fault condition. So I guess the question is then, where does that leave us now and what further tests can we do? So since the last video, there are a few updates. I have actually got some new tools which might help us with the diagnostics on this. So first up, you might have already seen this because I did make a video showing it. So if you want more details about this, then go and check out that video. But I have the SensePeak board holder, and more importantly, I have their probe system. So this system is absolutely fantastic. It gives me magnetic holders that I can attach onto this base, and I'm able to probe various different positions on the motherboard. So we might be making good use of that in this video. And the second thing is that Grandpa's Bench also has sent me an oscilloscope. So check this out. I am so grateful that he sent me this little oscilloscope. Now this is a Finersi. The model is a DSO153, and this is a really nice compact little unit. You can see here it's got like a nice little kickstand to it as well, and at the top we have a DSO and a DDS port, because this one, as well as being an oscilloscope, it does also have a signal generator function on it as well. So first of all, I think what we can do is use the oscilloscope that Grandpa's Bench has sent me to kind of prove this phase shedding theory, to see whether just phase 1 is activated and the other ones are turned off. So if we test the first MOSFET and we can see, yes, it's getting its PWM signal to turn on, but the other 3 MOSFETs are not getting their PWM signal, then it's very likely that that's what it is, the phase shedding. If for some reason that the other 3 phases are getting a signal and they're still not heating up, maybe there's issues with the MOSFETs and something there. So definitely this is going to help us, and we should try this first of all. Now I do have the oscilloscope. So by the way, this is the first time I've ever used an oscilloscope, just to be clear, so you're going to have to go easy with me on the comments because we might be getting this wrong on here. And yeah, if you've got any useful suggestions or advice, then let me know. So just a note about this oscilloscope, it is a 1 megahertz oscilloscope. Obviously it's a tiny little unit, it's not a bench oscilloscope, so there will be limitations. We won't be able to fully analyse the PWM signal and see it properly, but what I'm just hoping is we can check for a presence of it. I just want to know if it's there or not, and so hopefully this oscilloscope will at least allow me to do that and see whether that signal is missing or if it is present. Let's start things off by booting this up and giving it a go. So as I say, it does have oscilloscope and a signal generator. So I guess just to get used to the oscilloscope, we can put it into signal generator. Pressing down. I think there was a button up here. Yeah. Okay, so we got like a little toggle switch. This is similar to other Finersi products actually. So yeah, you go up and down on the menus. Let's open the signal generator. And you'll see here we can select, you know, various different waveforms on here. So should we do a step wave? That looks interesting. So yeah, it's got a frequency 1000 hertz on there with a duty cycle. So how do we turn it on? Run. Okay, so it looks like it is actually running. So let's see if we can go into the oscilloscope mode. Probably we hold it down, yeah. And oscilloscope. Okay, so let's connect the probe and see if we get anything. The signal generator, I'm assuming, will come out the DDS port on here. And we have some alligator clips for that. So that's great. So the oscilloscope probe has a BNC connector on there. And then we do get an adapter, so it's a BNC to a little RF one. So I'm not sure what that is. A TN, is it TNB, TNC, something like that. I don't know exactly, but we will use that adapter. We'll connect that to the DSO port. And let's see if I can zoom in a little bit. I'm guessing that this kind of probe is pretty standard as an oscilloscope probe. It's got like a little push down hook thing on it, and it does have our little grounding place in here, and we do get a little grounding clip. And we have a switch on here, and I've set that to 10 times because we obviously don't want to load the circuit while we are probing on here when we're going to make our measurements. So let's connect this to this signal generator. I guess we put the ground to the ground, and then we touch the probe here. Oh, you see that? Yeah, we do have our step signal. That's cool. Let me just change that to another signal. Can we do a sine wave? There's a sine wave. So that should be on. And back to our scope. And there we go. We've got our sine wave as well. So I think that's going to work fine. So for demonstration purposes, I think I will leave the oscilloscope actually on the board there. It's a fully plastic body, so it shouldn't interfere with anything. And let's get a ground on the motherboard here. Okay, and we should be good for probing. So I guess the next question is then, where do we need to probe to have a look at this PWM signal? So let's just have a quick reference of the board view. That would be the easiest way to find it. Here is our board view then, and we can see the CPU in here. And we did look at this last time, but if we zoom in down here, the first one in here is CPU SoC, so that's our system on chip controller. And then we've got our 4 phases, 1, 2, 3, and 4. And we knew that phase 1 is getting hot on here, PH1. And we've got the driver MOSFET that goes with it to power on this phase. So we need to have a look in the pins on this chip and find out where our PWM signal is. So if we look down here somewhere, let's have a look. Oh yeah, pin 26, PWM1. So if we click on that and we can zoom in to confirm. So this is CPU PWM1, and that signal is going to pin 26 on the corner of the driver MOSFET, and it also goes down here as well, TP66010, same CPU PWM1. So that's a test point at TP, so that's great. That's going to give us a point to measure, and then if we do follow the line up, that's going to go to our main PWM controller. So if we zoom in and have a look at there, here we go, CPU PWM1. And we can actually see on the controller, I can see to the left here, PWM2, PWM3, PWM4, and then we've got the SoC PWM. So we can see that they're all located towards the bottom of the chip here. And I guess in the other phases are all the same layout. So yeah, we've got a test pad here. We can see it's going to the same, and then for the next phase, another test pad and another test pad. So it looks like we're going to be quite okay to measure them on these test pads. So the way we should tackle this is first test this one, because we know that this phase is heating up, it is getting warm, 100% we should have a PWM signal present here because it's coming on. So it would be a good test for the oscilloscope, because I haven't used it before, just to make sure that I am able to measure a good PWM signal that I know is present. And if we get it there, then we will measure this one, this one and this one, just to confirm that they're not on, which kind of indicates that the phase shedding might be in place on this CPU phases here. So let's just confirm that everything on the board view matches with what we see under the microscope. We'll have a quick scan under there. And straight away I can see the test point on here. So you can see this little dot on here is the test point, and that's required because you wouldn't even be able to test on that pin 26 because it's under the chip there. So yeah, our test point is going to help, and you can see, look, the little via that goes off in there, and then that's the same layout. Obviously we've got a bit of thermal paste on there, and we've got another test point here and another test point there. So that's where I'm going to be testing. I'm going to be putting my probe on these test points, and we'll see what we see on the scope. So hopefully we're in a good position where we can see now. I'm connecting my power back up to the board, and that is connected. I'm going to trigger on the board. Okay, so I have triggered on the board, so the board is definitely coming on. I'm a bit zoomed in, but I have got my chipmunk connected so I can see. So let's have a little probe then here and see what we can see. Oh, can you see that? So we definitely have a signal on there. As I mentioned before, we're probably not going to be able to understand the signal with a scope like this, so ignore the fact that we can't really see the nice waveform, but I can definitely see a signal is present on PWM1. Let's move over to PWM2. And there's nothing there. Absolutely nothing. PWM3. Okay, so I am getting activity on PWM3. Let me just confirm again, PWM2. Oh, okay, so we are getting it on PWM2 as well now. So maybe they have come on. PWM1. Just let's see if it looks different or not. Yeah, PWM looks different. As I say, I can't really make it out on the oscilloscope what it is, but definitely there's a different signal on PWM1. I've just restarted the board and double checking it, and yeah, look at that, look. You can see that is the phase 3. I don't know if you saw that behaviour, but that looked like when the board comes on, it did come on with a normal signal, and now it's gone. But if we go back to phase 1, it looks like we've got something on phase 1. It's too quick, look, for the multimeter oscilloscope to pick it up, but I can see, look, the waves on there. You'll see that they are like a square wave probably. So I think actually what's happening here is that the phases initially come on for a few seconds when the board starts, and then they turn back off again. And then we just get like a little burst on there, but it's not really on. They're not constantly on. Whereas phase 1, there's definitely something on there. Look, you can see constant on the screen. So I think that confirms it to me. So what I'm going to say is happening here is when we initially power on the board, boom, all 4 phases come on for a little time, and then it drops back to a single phase on there, like a power saving thing probably. To be fair, I can even feel with my finger there is the heat in phase 1 again, but not in the other phases. I can't feel anything in those, but there's definitely heat on phase 1. So to me, that's very helpful, and I'm super grateful to Grandpa's Bench again for sending me that oscilloscope. It really means a lot to me that somebody would reach out and do that kind of thing for me. Yeah, I don't know what else to say about that other than thank you. So I think that gives us a little bit more to go on then. So let's move over to the next stage. I'm going to take a break for 1 second because somebody has just messaged me and they mentioned that they had a similar issue with a Ryzen CPU, and it actually ended up being the capacitor that was mounted on the top. And we haven't actually done a visual inspection. I just realised that. So we do need to try and peel away the cover here just to reveal the capacitors on there. And let's just double check that there's nothing obvious in there. No cracked capacitors or burning or anything like that. I'd just like to do a visual because I say we've not done that yet. It is definitely full of thermal paste in here, so I'm just going to try and clean this up to the best of my ability. Fortunately, it's stuck on pretty badly. I'm going to use a bit of alcohol just to try and loosen it up, I think. In fact, we'll clean up the die as well, and we can just do a full visual inspection, make sure there is no cracks or anything on this CPU. Especially now it's looking likely that there could be a CPU issue. I'll come back to you when this is fully cleaned. Right, we are cleaned up to the best of my ability, and looking at it, I don't see anything too obvious on here. We do have a little bit of a swirl pattern here, so it's quite a uniform one. As you can see, there is a bit of a reflection from the microscope, but just here, it's circling and going out, so I'm not sure if that's like been a heat spot or something, a bit unusual. If I compare it to another Ryzen CPU, there's nothing like that on this one particularly. So yeah, I'm not quite sure there. I was wondering about here because it looks like it might have been like a bit delaminated or something, but that part is exactly the same as well on another CPU. It must be where the plate here is, you know, glued down. So I don't think that this is anything to worry about. Let me zoom in and just have a real good inspection of these capacitors. Okay, let's have a little look then. Down here. Just looking for any that have got maybe any visible cracks from the top. Or potentially, you know, discoloured compared to the rest. I think that's looking fine. Yeah. And we're back round here again. That looks fine. I can't rotate it really and look at an angle because we're still all clamped down on the board holder on here, but I don't see anything too alarming at the moment looking at that. So let's discuss what else we can check to rule out the CPU, because I've got a few of my own suggestions that I would like to try on this. So this CPU is using the monolithic drivers on here. These are made by MPS, Monolithic Power Systems, and it's not just a MOSFET driver. They are more like an IC on here. They're quite intelligent. So let me just show you these under the microscope, because there may be some more checks that we can do, and we'll discuss how we're going to be able to do that. So the CPU is using these monolithic drivers, as we said, on here for all of them, even including the SoC and this one as well. I can't remember what that was. We've got them all. That's a slightly different package than the others, with a smaller inductor. But all of these are being controlled. They're all being controlled by this guy. This is our main PWM controller. I think we'll actually have to look at this under the schematics just to understand exactly what's going on here. So let's go back in and take phase 1, for example, on here. So I'll show you a few important things on this chip. So first of all, if we look at pin 8 on here, what you're going to see is that goes off all over the place, and the reason for that is that's the 3-volt power supply on here. So if we look at pin 8, it says P3 V3. So this is our 3-volt on here, and reason why we've got a 3-volt on there is because, as I said, this is quite an intelligent driver, this monolithic driver, and it requires 3-volt logic to power it and control. So as well as giving out the CPU V core out of these ones here, we can look at some of the other pins that are on here. So let's go to the bottom, and as we've already discussed, that's our PWM on that first pin, pin 26. But then we've got other pins on here. So we've got a STB, so that's some kind of standby. But then these ones are quite interesting to me. We've got the CPU CS, so that's going to be our current sensing. So it's going to be looking for any kind of overcurrent, conditions on here, over voltage conditions, and it's going to be reporting back to the PWM controller if there are any problems. And the last one we've got on here is the temperature one as well. So that's going to be reporting constantly its temperature, and if it reaches over a threshold as well, the controller's going to be having the ability to shut things down as well. So it could be one of those conditions that's happening. Maybe one of the MOSFETs is faulty on here, MOSFET drivers, and it's reporting either wrong, or it could be reporting correct, and we've got a fault elsewhere. But maybe we're getting a current sense alarm or a temperature alarm that is causing this particular issue, and definitely that would cause the laptop to restart. So my plan of action is, if we can actually log in to this controller, we'll be able to see everything. We'll be able to see if any of these phases are reporting any alarms at all. And we can also keep it on, keep monitoring it until the laptop crashes. And when at the point of the laptop crashing, we can see if it triggers an alarm. And if it does, obviously we know that there is an issue around there. So essentially we are testing every single MOSFET at the same time on here, and we're looking for any fault conditions at all with the power stages for the CPU if we log into there and we check the alarms. And we can do that in real time, I believe. So that's what I want to work on now, is getting connected and see if we can identify that maybe there is an issue there. The question is then, how are we going to connect to this IC? So let me put a picture of it on the screen. So we can see down here in the corner, we have the MP2845A. That's the PWM controller that we want to connect to. Now, believe me, I've checked on the internet and there is no public data sheet available for this chip. And I even emailed MPS and they weren't willing to give it to me, unfortunately. Now, I do have the board view for this board, but I don't have the schematic. So it's difficult to get details of this exact chip. That being said, this motherboard is not the only board that uses this chip, so we can reference this MPA chip on a different board. So if we go over to my database, search for MP2845A, we can see it here. So we can see it is a monolithic power system, MPS, and we've got the package size on here. It's a 56 package, 56 legs on there, 7x7. And yes, we've got the main chip marking is an MP2845A, as we've already seen. System PWM controller. We've got an image of it here. So that looks exactly the same as our chip. Brilliant. And it is a programmable IC, as we can see on here. And if we look on this section, data sheet, we've got a PDF here. So let me open up that. And so here I've attached a page from a schematic, which also uses this same IC. So if we zoom in so we can see what's going on. So down here you can see it's the MP2845A, exactly the same as ours, and we are able to see a little bit more information. Now we've got this, we can see each pin on here and what they actually go to. And we're going to need two different connection points. Oh, here we go, look, these are our PWM signals that we saw on the board view. So to connect to it, we're going to be using the PM bus, and we're going to need the serial clock and a serial data to connect to it. So we can just have a little search around on here. And here they are. I can see them. 35 and 30. Let me zoom you in a little bit more again. So you can see quite clearly pin 35 is SCL for serial clock, and pin 30 is SDA for serial data. So all we need to do is connect up to these two pins on here, and if you have a look on there, they are going to go through a resistor on here, a 0402 ohm, a 0 ohm resistor by the looks of it, and I think it's going to give us some information on here, SM bus, you see, and it also says 20 on the SM bus there as well, so that's probably the SM bus address that this laptop's using. I don't know if my laptop is going to be exactly the same as that or not, quite possibly. So I think we can go over to our board view and look for this 35 and 30 and see if it matches with what's here on this schematic, and then see if we can find that on our board. Here we are back in the schematic then, so let's zoom out because we were on the MOSFET. So if we go up to here, U660000, and what did we say it was? Pin 30 was one of them. Here we go, SDA. So let's have a look where SDA actually goes on this board and see if there's a good place to connect to it or not. Well, it looks actually like it goes straight to a resistor. In fact, even better than that, from this resistor, it goes to a test point here. So we've got, let me zoom you in, an SDA and an SCL, two different test points. So that's going to be really easy to do. And obviously, it's similar like the schematics on the other laptop, it goes through this resistor here. But we're going to be looking for those two test points on here. And which one is the data? The top one. Top one is data, bottom one is clock. And you can see in relation to the chip, they're kind of like towards the top left-hand corner up here. So that's brilliant. I think we know what we're looking for. Let's bring in the microscope and see if we can find it. So we're focused in on the controller here, and as we said, towards the top left on here, we've got two test points. I can see them both here. So we said the top one is data and the bottom one is clock. We can see them both here. So all we need to do is connect to these two test points, and hopefully we should be able to read the controller. So I'm excited. It's time I finally get to use my new probes. So let's connect those onto the magnet. I'm just going to put the green one on the top, yellow on the bottom one, because I'm going to do green for data and yellow for clock. Might need a little bit of help from the microscope to line them up again. So my green for data is going to be on this top test point here. Nice connection. And our clock, which is my yellow one, is going to be on the bottom one here. So maybe we'll just go a little bit more central with it. Nice sharp probes these. I think we're set. And the interface to connect to the PC, we're going to be using the ASUS MPS PM Bus Programmer. This was very kindly donated to me via ASUS, so I really appreciate that. Thank you very much. And I've already done a little video in detail, as I said already, about this. If you want to know a little bit more information about this, definitely check out that video. If we look at the programming header on the side here, data is at the bottom and then clock are above it. So green for data, is connected there. Yellow for clock is connected above it. Perfect. We do just need one more thing, which is a ground. Also included with the programming set is I get this one, which has got a banana jack on it. That's ideal for getting my ground. So if we check, the ground is actually in the center above the clock here. So I'll collect the black one in the ground just here. Just to make it easy to connect the ground to the motherboard, I do have this one that I've made up before, which has got the 4mm banana jack, and we can just get the ground from the USB port. Did also make a video on how I made that as well. So I'll just need to connect that into there and stick that into the USB port. That is all connected. We are set to go then. One thing you might notice down here is that there will be some little activity status LEDs. I don't know if you can see them in the light, but there is a blue and a red one in there. So I'm going to keep an eye on what's going on there. I've just readjusted my probes slightly just so I could get the heatsink fitted back in. My USB is connected, data and clock is connected, my ground is connected. I think we are all set to go. The only other thing is the software. I will just show you the software side of it as well, because if you do want to do this kind of thing for yourself, it might be a bit confusing if you've not used the software before. So let me show you that on my desktop of exactly what we need to do. Here is my desktop then, and in my MPS resources, we have software in here. And important in the MPS software folder, we have a README. Let me zoom you in a little bit on the README file. The important thing to know then is that within this text file, it's going to list all of the MP chips and which piece of software that you need to use for each chip, because there are different pieces of software. So we need to find our chip, which we can still see in the corner there of the screen, which is the MP, look under the line, the 2845A. The easiest way then is if we just go Control F, type in MP 2845. Let's just search for that. And here we go, I can see it there. So it looks like it comes under Computing and Telecom Core, MP2845, and also includes the 45A as well. So both of these ones are going to be programmed by the Computing and Telecom Core program. Now this one I've not actually installed on my computer yet, so I'm going to go ahead and get this installed, and then I'll be able to run the software. Only takes a second. And we can launch it. Ooh, very nice. Okay, so it does say connected at the moment. The board is not currently powered on. Let's just click scan, just see if it sees anything without the board being powered on. Looks like it's got a progress bar down the bottom here. It's scanning for something. What I'm hoping is the case here is that we can read it while the motherboard is actually turned on and while, you know, the rest of the computer is speaking to the chip itself. So yeah, the scan took quite a long time and it didn't find anything. I was kind of expecting that because I believe that it does require power. It's not powered by the, you know, clock and data line itself. It does require the logic power to power up the IC. So that makes sense. I'm going to power on the board now then with standby power only. Okay, we are plugged up with the charger. I haven't booted the board. We're just plugged in with standby. So let's have another scan again and see if we find anything. Oh, here we go. We found it. I have just had to power on the board actually, so it looks like it won't work on standby. But anyway, that's what we want. We want it to work while the board is powered on for our monitoring. So you can see now it's identified MP2845. And it also says 20 on there, which matched the address that was on that other schematic. So let's select that. And how do we connect to it? Oh, okay. So this is slightly different to the other ones that I've used. So you select it so it's red, and then you click the buttons under here. So I guess we click monitor and see what that says. Here we go. Here we go. We're pulling in data. Yeah, so this is a slightly different layout. So the different MP chips have a different software on here. Now, before I do anything, what I would like to do is, because I can already see a lot of information here, I want to read the register on this. So here we go. This is the configuration. So I want to back up this chip, and this is what I'm also going to do on every single board where I come across a controller like this. I'm going to take a backup of it, and we're going to be sharing this in the database. The reason I want to back up this config is to help, you know, myself in the future, and especially to help others as well, by building up a database of configurations for these chips for different laptops. This is really important because you can buy the chip and solder it onto a motherboard from AliExpress and it's not going to work. And then you're just going to assume that, you know, it's a bad chip from AliExpress. But no, it needs programming, this IC. And without the programming on there, it's not going to work. And these chips can be used in various different things. It can be in a laptop with an AMD or an Intel or a GPU, and it needs to know the core information, really, like how many phases there are, for example. All that type of information is going to be stored, and a lot of different parameters are set as well. So it's really important to take these backups. So let's do an export on here. We'll go for a system export, and I'm just going to call it X for now. I'm going to name that properly later and add it into the database of dumps for all of these chips. And we can see that we have successfully exported that file, so that's great, and I'll be able to share that with people. Okay, so let's get back into this monitor screen then, because this is going to be the screen that we're really interested in. Now let's analyse what we can see on here. There are a few things that I can quite easily point out that it looks like are quite obvious. So we've got system fault in here. Obviously we've got all green lights currently, so that's brilliant. That obviously means our system is running with no alarms. And we've got input alarms on here. So this one is going to be voltage in 0 volts. So I'm guessing if the voltage in completely drops, this light's going to turn red on there to indicate that, we've got 0 volts. If we don't have a complete loss of voltage, then we've got voltage in UV. So I'm guessing that's under voltage on there. And again, that one's green. We've got die OTP. Now, I can't really hazard a guess at what that is, but to me it's green, so we're good. It's just something that we can monitor, and if for any instance when this laptop crashes it goes red, we'll probably have to research what that means, but leave it in the comments if you do know. And then we've got 2 MTP alarms on here. So we've got an MTP CRC, so I'm guessing that means cycle redundancy check on there. So if it's detecting any types of critical errors on there, it's going to put those 2 alarms on here. Got MTP general error, but again, these are actually for the main input and the main chip itself, not the outputs. But we've got a nice little status here that we can monitor. This is brilliant. And then we've got 2 voltage outputs on here, V out 1 and V out 2. It looks like V out 1 is not currently enabled because the power state is red on there. So that could be normal, and obviously we're going to have the other alarms associated because the output is not even on anyway. And voltage output 2, that one is on because we've got a power state on. And again, these are looking familiar to me. OVP is going to be over voltage protection. So if the voltage increases, I'm guessing that's going to go, oh, did you see that? That power state went on there for a second and then went off. So for some reason, we've got something there. Why did that power state go on? It went on for a blip and then went off. So yeah, let's continue just going through what these alarms mean, and then we might come back to look at that. Maybe that is a problem. I'm not sure. Maybe this voltage out 1 actually should be enabled on there. In fact, you would imagine that the output 1 would be enabled before the output 2, but I'm not quite sure until we work out exactly what it is. So yeah, we said over voltage protection, and then again we've got UVP, under voltage protection on there. So if the voltage falls below a certain threshold, that one is going to go green. So yeah, if something was partially shorted on the output, I would expect that the voltage would drop and we maybe get that under voltage protection alarm. And then we've got our current. Oh, did you see that? I didn't press that voltage out, just kind of blipped again there. Oh, under voltage protection. I just saw that come on. Don't know if you saw that. Yeah, we've got something going on here. Let's continue again with the alarms. Over current protection is green on here, and OTP will be over temperature protection. So we've got current and temperature. That's what I believe. And then obviously VR hot. If you work on laptops, you probably already know that about this signal, the VR hot. But we've also got a DR MOS alarm on here, and a line floating. So I'm guessing that means open circuit, and DR MOS must be the actual MOSFET inside the MOSFET driver. Maybe if the IC detects an issue, it's going to put something on there. Now, interestingly, we don't read any data on here at the moment because I'd like to have seen the temperature and the actual voltage, so I'm wondering why it's not reading that at the moment. What have we got further over here then? So we've got rail 1, current sensor 1, I'm guessing that is. Rail 1, current sensor 9, but we've got no data in there anyway. And we do have a trend graph or something. Maybe that appears in there. I'm just going to have a quick scan of the other settings here and see if there's any more information that will be useful. I'm guessing the monitor page is where we really want to be. This is where we're going to actually check the settings on there. Okay, so this is interesting. We've got Vout1 says phase 1. Vout2 says phase 0. So that makes sense then. Vout2 is actually phase 0 because they probably don't count 1, 2, 3, 4. They probably count 0, 1, 2, 3. So it counts from 0, the phase, and Vout2 is going to be 0. So if we go back to our monitor, this is Vout2 on here for our first phase, or phase 0 in this case. So Vout1 is the actual second one. And oh, that wasn't me. I just seen that. So maybe it is kind of turning on and off Vout1. It looks like it's trying to do it, and maybe it's not actually succeeding. I'm not sure, because I've seen that blip a few times since we've been on here. I don't know if you've seen that as well. So the settings are going to get quite advanced here. We've got frequency, gain, steps, volt out, CMD, boot, DVID. So honestly, I don't really understand all of these, but one that's striking out to me is Vout2 for phase 1 is 0 kilohertz. Vout2, the frequency is 160 kilohertz. So yeah, your guess is good as mine. Why this frequency is different between the two phases. Maybe that needs to be or not. I'm not going to mess with these settings because I don't know what I'm doing in there. And funnily enough, that's actually the basic screen. Let's check the detailed screen then. So Vout1 settings, and we've already determined that it's actually Vout2 is for phase 0. So you can see in here the settings, they are going to be probably similar. Let me just keep switching between them, see if I see any differences there. 20, 0. Actually all looks to be very similar. What's current configuration? Okay, well you can see in there for yourself, function en, function enable. So a lot of these are not ticked in here, but we have got PWM fault ticked as enable on here, and PWM fault ticked as an enable on here. So maybe this is just turning on and off alarms on here. Current detection. So you've got really advanced things again with different ripple information in here. Thermal and GPIO. What about protection? Oh, okay, so this looks a bit more straightforward. So in protection here, we can see kind of the parameters it's set to. So of over voltage and protection fault on the voltage in is set to 13.5 volts. So I don't know what, it's maybe 5 volt logic or 3 volt logic or something like that on here. Voltage in on is 0.25 and off is 9.3. Okay. So when it detects anything above 0.25 volts, it's going to be detecting that there's a voltage in present, and if it goes over 9, then it's going to be off. And you've got temperatures on here, Vout and Vout2, just to show you them. But anyway, let's go back to the monitor because that's what we're interested in really. Oh, I just saw an overcurrent protection there. Don't know if you saw that. So let's try rail 1 current sensor. Oh, okay, we're going to get some information now. But it's flatlining. For some reason, it doesn't allow us to see any current information. So that's kind of a shame. What about rail 2? No, also doesn't give us anything on there. More faults. Crikey. We've got a lot of alarms on here. Right, I'm not sure on there. Let's go back to the basic monitor screen. I'm going to stop it plotting. We don't want anything to do with that. Can we clear it? Whew, well, so we got a lot of information there. Let's plug up the HDMI and see what this is actually doing, and I will put that screen on there at the same time. Let's see if we are in the BIOS currently, because I can't see what's going on, and if we are in the BIOS we can try and trigger a fault on here and see what it does. I've set up my screen for you so we can hopefully see everything at the same time now. So we've got up here the picture, and down here we've got the MPS software. So let's plug in and let's power on again. By the way, I didn't have a HDMI image on there, but the HDMI cable wasn't plugged in to start with, so I think it might only work with the HDMI connected at the start. Okay, I think we've got picture coming on. And we are into the BIOS screen. Perfect. So currently on the BIOS screen we are looking healthy. Down here we have no alarms at all. Okay, so power state has turned off for VOUT1. Interesting. Maybe as we've previously seen with the oscilloscope, that the phase 1 and the other phases came on to start with, and then they, phase shed and dropped back down again. So maybe that's what's happening on here, because it does look like the output is switched off on there. So let's boot from a USB stick and let's try Windows. I'm going to boot into Medicat, boot into Windows, and let's see if anything happens when this laptop crashes. What I'm going to do is I'm going to power down the machine completely. There we go. Oh, and did you see that down in the bottom corner? So yeah, the power states are off at the moment. I just want to see that again to see if in fact, I'm going to let it cool down just before I do that, but I'm interested to see if what I'm expecting there, that it's just VOUT1 that comes on at the beginning and then turns off again. Yeah, it's been running for a bit long on these little heat sinks. These are getting red hot. So I'd prefer things to cool down before we do anything, just so we're not introducing any new faults. We definitely have to work with these heat sinks rather than the factory heatsink and fans, because we wouldn't be able to do what we're doing now and probe it with the assembly attached on the laptop. While we're just waiting for things to cool down then, let me just give a shout out to a couple of people, because I've actually had some new members join since the last time I did a video. So I really appreciate your support, guys. And let me just read out the names, because we have the Tech Flipper, who I know also has a YouTube channel as well. So I appreciate you coming over and being a supporter on my channel. And if you would do him a favour and go over and subscribe to him, I'm sure he would be really appreciative of a few subs. And we have Radical as well with a 4 for the A. I like that. Pega, we've got Lee Dawson, we've got Stefan, and we've got Henzo2 007. We've got the secret agent at the bottom. So thank you guys, massive shout out to you and for supporting my channel. I really appreciate it. I don't know who a lot of you are as well, so if you wanted to reach out to me and have a little chat, yeah, please by all means do that as well. I'm quite open to that if you want to message me on Discord as well. And of course, we can't forget the JFix Legends as well. We have 2 this month. We have Gear Anderson at Let Us Repair. So thank you, and I hope you're well, mate. And we also have Grandpa's Bench, of course, who sent us the oscilloscope. So again, a massive appreciation to you. You've helped my channel in more ways than one, so I really appreciate that. So where are we at? Oh yeah, we have cooled down quite significantly. Look how many things I've got connected on here. It's getting crazy now. Okay, let's try a boot then and see how we get on with the alarms. Okay, I've had to have a bit of shuffle around because I forgot to connect the daughter board for the extra USB port. So we've removed that one adapter so I can plug my mouse and keyboard into there. See if the keyboard and mouse is working. I can go up and down. Let me see if I can work on this on the small screen, because I really want to see what's going on down below. As you can see, by the way, voltage out 1 did turn off. So let's go back into what are we doing on here. Let's go to live operating systems. Let's try mini Windows 10. Or should we try Sturgis Stelic? That worked, didn't it, last time? Let's try mini Windows 10, see if that one causes the system to crash. So we are booting into Windows 10. Let's see what's going to happen here. Yeah, we do have a mouse working, and I can see things flashing down below. Interesting that it just comes on for a blip and then goes straight off. Okay, so we'll use this interface because this is the one I'm more familiar with Medicat on here. Now I'm wondering if it will let us do a driver install. Let's try Snappy Drivers and see what that does on here. We've got basic display adapter. That's what I really want, is just to get a bit of visuals so we can get a better resolution. Right, I've clicked install. Let's see if it's going to crash or what's going to happen. I have no idea. Usually the mouse stops working before it crashes. Here we go, it's crashed. Did you see that? That caused it to crash. And look down below. I didn't see anything happen on there. Let me go back to my main MPS window. Yeah, I'm not seeing anything obvious in there at all. Everything looks fine. So yeah, we are going back to the Ventoy screen again. Right, let's power down then and readdress. Now, I wasn't glued to the screen when that did, so I'm going to actually just save and analyse the footage and come back to it, just to see if there was anything that I missed on there before that happened, because I wasn't quite ready for it, but I don't believe anything appeared on there. I don't think we had any extra alarms. Okay, I've just watched back the footage and I missed something. So just before the laptop crashed, when I watched it back, I could see that it actually did try and enable that second phase. It came on for a second, and I think it was either over voltage, over current. One of those alarms was on, and then it just dropped back straight away. So I believe that there could actually be the issue. We might be onto something here. Maybe for some reason it's not able to enable and boost up and use the other three phases available. As soon as it does, you know, it seems to switch back off. And I've seen that quite a few times while we've been looking at that screen. It seems to be like flicking on and then just flicking off. I've never seen it stable yet so far on that screen. So yeah, maybe we're onto something. So potentially then, if we are correct, this phase here is fine, we know that, but when it tries to activate this one, or this one, something's happening. So how can we kind of identify which one of these is? Because when you take measurements, they all kind of very similar because they're all in parallel. It's very difficult to distinguish between them. And we can't really inject power through these MOSFETs because they're not shorted. So power's not going to pass through. We're not going to be able to see that under the thermal camera necessarily. I think the only way we're going to be able to do this is by removing one by one each of the phase, or disconnecting each phase one by one, and then we can see maybe when that phase tries to turn on again, it actually stays on this time with the faulty one removed. Now, rather than removing the MOSFET itself, there might be an easier way to disable these. So we will just examine a schematic diagram for these and see if we can actually disable the output on here, rather than trying to lift up the coil or remove the MOSFET. Yeah, we might be able to disable it by pulling off a resistor, for example. I know you can't see very well the markings on there, so I've got a bit of a better picture from the board at an angle, so we can see them here. That's what they are. Got this one, or this one. That's potentially suspect, these three here. So you'll be able to see on the image there in the bottom left-hand corner, that's one of the driver MOSFETs, so it's an M86949. So let's go back to the database again, and we go 8, 6, and we go 4, 9 here, main chip marking. And if we have a look at this one, we've got an image of it. So yeah, you can see the footprint on here, how it looks. And I'm interested in the data sheet now. Again, this is not in the public domain, any data sheet for this IC. So the best that we can do is download a schematic. And the schematic is for a different board, but again, we can see on here the chip itself is an MP86949. So we've got the same IC that's utilized in this schematic. So this is kind of useful for us. And we get an idea now of actually how the circuit is built, looking at this, not just the IC. So we can see in here that we've got our inductor that obviously goes to the processor on here. So there's the coil. And if we look on here, so that's the switched output on pin 9. And then between 32 and 33, it's going back on itself. So that's the bootstrap here. And there is a few components in this circuit here. So we got this resistor here, PR8114. Obviously that's not going to be the same on my board, but the same principle. We're going to have a capacitor and a resistor. So I believe that the BST, the bootstrap, is the pin that's responsible for pushing out the voltage to drive the gate. So the bootstrap here will go back through into the phase, and then that will activate the switched output. So yeah, definitely let's have a look for pin 33 and see where that goes on our board view, and we can try maybe desoldering that one to disable the output. So pin 33 here. Yeah, this is the one that doesn't have a label on it, so we know what it is now from the schematic. So it goes into this resistor here then, and from that one it goes into this capacitor and then goes back out to pin 32. So yeah, you can see, look, it's doing a circle back in from 33 to 32. So on the board it's going to be this resistor followed by the bottom right hand corner. So I think that's pretty straightforward. So over to the microscope, and I can see it on here as well. So it's this resistor here, obviously comes in through there, and you can see like how it goes back on itself there. So pin 33 to 32 inside the chip, and that's the same for each one. Same here, same here, same here. So we don't need to touch this one because that one is definitely working. And we want to try and rule out one of these then. So should we just go through them in order? Let's try this first one, and then we'll go and change it and try these ones. I've rotated the board just to attack it from a better angle that's more comfortable for me. So yeah, we'll do it from this angle and then probably just shift it down. It does feel good to finally actually be getting the hot air station out on this board. Okay, we've just shifted it over. So just to confirm, that's the first phase and this is the second phase, and we've moved the resistor off its pad there, so it's not going to get the voltage now to drive the gate. So I think that output here should be disabled. I've just put the probes back in position and we'll connect the programmer up again. If we are actually correct on the money with what we're saying here, we do still only have a 1 in 3 chance of it being the right one, so chances are quite low that we're going to get it on the first time. But let me bring the software back up again. Okay, we do have it here. We'll make it a little bit bigger like that so we can see it when we get the picture on. So okay, I've seen it initialize to start with. Don't know if you've seen that. But from what I understand, that this is normal on the startup process, that the actual other phases come on and then the phase shed and just cuts them off straight away. So that could be quite normal behaviour. Unfortunately, we are not going to be able to use this method, I don't think, to test it because I'm unable to get a picture. As you can see, the board isn't properly booting. I have triggered the board, and we can, when I've triggered the board, it does come on because I can start speaking to the controller again, but it doesn't even activate phase 1 on there. So there's definitely an issue. It must be too intelligent, and it realises that there's a problem there, and it just doesn't even enable the first phase anymore. Just to confirm then, after putting that resistor back, we are back to the working state again in the BIOS here. So we need to come up with a plan of action now. Looking at the clock and how long this video's been going, we are already, quite into it. And I don't want to make the video crazy long. So I think what we'll do is probably leave it at this point. I think that is the best course of action, and we'll get a bit of feedback just to see, what you think to what we've done so far. But what I've done is previously I've ordered the MOSFET drivers anyway, so I'm still waiting for them to arrive. Ideally, if they were already here, I would just replace all three, and I think that's what I'm going to do. Then there's no guesswork involved. So yeah, next video, part 5, it's going to be now. We will just bang 3 new MOSFET drivers in there, and then at least we've ruled that out as one of the possibilities, and then we'll go down the avenue of exploring some more ideas, I think, as well. I am super impressed with the PC bike kit, and I don't know if you watched the video, but I mentioned that I didn't have the little rubbers, the black and the red coloured ones that went with the other probes. So I did actually message to SensePeak just to ask them about it, and they have agreed to send me some as well. So yeah, kudos to them. And not only that, they've also agreed to send me some oscilloscope probes as well. So I'm thinking, wow, that's amazing. I will definitely be showing you those ones when they come as well. So we're going to have really got the full set, which is going to be, fantastic for doing any kind of more in detailed diagnostics. So I really appreciate those of you still sticking around with this one on this journey. It is a bit of a long road to get to the final destination, and I have listened to your comments, by the way. I just haven't got time to try some of the other suggestions you've put forward. So definitely we will be trying them next time, and we're not going to rule out anything still. If we do replace those MOSFET drivers and it still doesn't work, we might move on to the GPU then. And yeah, I've got a few ideas now about testing the GPU. So yeah, let's keep going with it. And yeah, I'm enjoying this 100%. So yeah, I'm going to keep going as long as possible on this one until we actually get a resolution.